We are delighted to present our research findings and share insights on improving and analyzing sketchy high-fidelity free eye drawing, reported by the first author, Lida Huang. Free eye drawing refers to using only the eyes to create drawings, thereby replacing using hands in conducting freehand drawing. This paper aims to improve free eye drawing by resolving the remaining problems associated with the previous studies and analyzing the usability of these gaze control methods in different aspects. The main contributions of this paper are fourfold. A fully functional free eye drawing user interface tailored for gaze interaction that enables high-fidelity digital graphics editing. A unimodal gaze control drawing manner, mimicking the natural brush start-stop action of hand drawing and a better way to make observations. A double blink gaze gesture that was adopted for free eye drawing and can be generalized to gaze interaction. User studies and system evaluations offer comparisons with different gaze control methods and real-world drawing by hand, facilitating recommendations regarding improving eye tracking techniques and gaze interaction. Today, the primary gaze interaction form is that what you look at is what you get. This method has two features. The gaze position or trajectories are immediately output as pixels. The applications that follow this method cannot conduct a click-and-drag mouse event. They can only execute mouse click events by a dwell click, namely, dwell click to draw, dwell click to end drawing. Thus, they can only create straight lines connecting the brush start point and end point. This type of gaze control is challenging for free eye drawing, as observation requires the eyes to fixate on the sketches, whereas controlling the brush requires the eyes to make saccades. Saccades require step-like changes and ballistic movements, whereas accurate brush control requires minor adjustments. To address the above problems, we proposed a novel gaze control method named Compass in our previous research, which emulates click-and-drag for drawing continuous strokes. A circular cursor can trigger the eyes to make smooth pursuits along its radius, drawing smooth lines and diverse shapes. The directional needle points from the brush point to indicate the direction of the brush movement. The traditional command for starting and ending a drawing is the dwell click, which means the user rests the gaze on a point for a prolonged period to activate or deactivate the brush. However, using dwell click to end the brushstroke is an error-prone approach as it will most likely lead to endpoint tailing in free eye drawing. Considering the challenge described above, we employ double eye blinks as an alternative method to end a brush command quickly. The application is built with C# and runs on the Windows operating system using the Unity engine. The interface aligns with Fitts' law of gaze control. For example, the buttons are 100 pixels wide times 120 pixels high. To avoid adjacent interface elements, the buttons most frequently used during the drawing process were placed in the screen's four corners. These buttons can be reached quickly and are distanced from the visual attention area, namely, the canvas, to minimize the chances of the user unintentionally activating the buttons. This application employed a dwell click of 0.5 seconds on the canvas to start drawing and a quick double blink to end the drawing process, while the command for button selection remains a dwell click, namely, 0.5 seconds. The pan canvas function adopted an auto-scroll capability, allowing the user to pan the canvas vertically and horizontally if the user looks at an active region. The four corner buttons were designed to remain continuously clicked after a one-time dwell click where the gaze stays on the button, avoiding unproductive mouse activities and shortening interaction time. We adapted the algorithm below to mimic the inherent brush start-stop actions in hand drawing. With this algorithm, the brush will not move when the user makes visual observations within the compass circle. Therefore, the user can pause the brush while conceiving the areas to be drawn and start drawing easily, replicating the frequent start-stop action in real-world drawing. Furthermore, the damping coefficient can restrict drawing speed at a similar speed to hand drawing speed. We applied a novel double gaze blink gesture to exiting drawing, which has higher accuracy than a single blink gesture and higher efficiency than the dwell click. First, we examined the eye blink frequencies for the two gaze control scenarios. The probability of two continuous spontaneous blinks occurring in fewer than 2.6 seconds is significantly low. Therefore, a time interval of less than 2.6 seconds for double eye can distinguish between an intentional command and unintentional eye closures. We also tested the accuracy rate for stopping drawing via different time thresholds in our application via Tobii i5. Table 1 shows that two consecutive blinks within 0.4 to 0.6 seconds is robust, as the double blink command conforms to eyelid movements in our environment and similar eye trackers. In the final application, we adopted 0.4 seconds as the default time threshold for a double blink click. In this paper, a drawing experiment, n=45, was conducted to compare three methods: the real-world drawing with hands, our method, and the previous method. The three screen recordings displayed here represent the results, drawn via the three experimental methods. Each participant was assigned a sample sketch and was asked to replicate the sample using the three drawing methods and try to produce as similar a sketch as possible through each method. The drawings via the different methods show that our application leverages the design of compass to enable smooth pursuit and easy drawing with the eyes. The fidelity is improved significantly compared to the previous gaze control drawing method and resembles the results obtained from hand drawing results. The previous gaze control drawing method in the experiment represented most of the gaze control studies were based on the form of dwell click to draw, dwell click to end drawing, where the gaze could only determine the start and end points, thereby limiting the user to creating a single line segment per interaction, reducing efficiency. The AOI results showed significant differences between each pair of groups among the three methods. It indicates the efficiency and engagement of gaze interaction. The AOI of our approach was significantly higher than the previous one. There are several reasons for the improvements. For example, by reducing the number of dwell clicks through both the UI and the double blink gaze gesture, the attention and productivity of the drawing process are enhanced. The improved compass and brush dynamics also minimize distractions from weak interactions, enabling the user to concentrate on the drawing task. 6.2.3 Ease of use. The raw NASA TLX scores indicate the participants experienced difficulty using different drawing methods. As shown in Figure 13, hand drawing exerted the most minor mental, physical, and temporal demands and was associated with the lowest level of frustration. The score of our method is suboptimal. Nevertheless, it significantly increased overall performance levels and decreased mental, physical, and temporal demand relative to the previous method. As the following step, the field study aimed to examine the usability and expressive ability of the completed application among our target users, people with a motor disability. It aimed to assess the potential of our method to accommodate individual differences among users. This study tested our completed application with target users of eye trackers in their natural environment, including homes or familiar places. Participants were asked to create illustrations according to their desires freely, and the data collected consisted of these illustrations. A survey, System Usability Scale, was conducted to quantitatively measure the final application's usability after the participants finished the test. In addition, a semi-structured interview was conducted, and the illustrations created by the participants were analyzed using thematic analysis. People with a motor disability who used eye trackers as their computer interaction tools were recruited via partnerships with the People's Hospital of Guangxi Zhuang Autonomous Region and the Disabled Persons Federation. The average system usability scale score among the participants was 82.75, labeled as very good. It indicates that our application was easy to use and enabled target users to emulate hand drawing. All the participants succeeded in implementing free eye drawing with our application, producing expressive visual works. The illustrations created by the participants included illustration art, simple line drawings, and cartoons. Despite being affected by different drawing skills among the participants, the drawings were satisfactorily executed, and no previously identified problems with gaze interaction were discovered. This is an example of using iCompass 2 to create illustrations by one of the participants in the field study. This paper presents gaze interaction design to enhance free eye drawing and develop professional free eye drawing software with abundant drawing functions. It also examines and analyzes the usability, including the performance in creating high-fidelity graphics, eye movements, and user experience with the implementation of the completed application. Through the improvements of this paper, the application achieves positive usability and sketch-level performance, similar to hand drawing. It also conforms to the physiological habits of hand drawing and achieves eye comfort. Our future work will focus on 1. Integrating interactive beautification systems into gaze control drawing, 2. Exploring various gaze control modalities for gaze interaction, and 3. Developing systems based on deep learning methods to address eye tracking errors. Thank you.